is. Okay, so we just started the recording, so all that you missed was number 5, taking derivatives, plugging in. So far, so good? And then we just have to use the Taylor series formula that says you're going to take a sum of the derivative evaluated at the point divided by n factorial times x minus a to the nth power. So this is the Taylor series formula, and this actually miraculously gives you the power series representation for whatever function you start with. So it's kind of interesting that, remember how we were trying to figure out what is the power series for this function or that function, always going back to a geometric series. This works for any function. Doesn't matter what it looks like. It'll always work out. Anyway, let's go ahead and plug these in. So the first 4 non-zero terms, okay, so I'll zoom back out in just a sec. So we're starting with that 0 up there. So 0 over 0 factorial times x minus 0 to the 0 is just 0. So we'll leave that out of it. But and then the next term, I'm using that 1 up there. So 1 over 1 factorial, x minus 0 to the first. I'm not going to write minus 0 anymore because we know it's just going to be x. And then this is going to be 2 over 2 factorial times x squared. And then 3 over 3 factorial, x cubed, 4 over 4 factorial, x to the 4th. So there's the first, let me just make this look a little prettier. X plus x squared plus 1/2 x cubed plus 1/6 x to the 4th. So there's the first 4 non-zero terms, but I think you probably could figure out what the pattern is. In fact, you didn't have to do this, but if you were tempted, you should succumb to this particular temptation to do this and say, oh, I see the pattern. It's always going to be n over n factorial times x to the n. And sure enough, you'd be right about that, that's the general form of each of those terms. Very nice. So there's that. It didn't ask for any convergence, did it? No. Just the first 4 non-zero terms. Oh, the next one asks for convergence, doesn't it? Wait. No. Yeah. I guess this tonight's stuff does. So any other questions about number 5? 5 look okay? By the way, I should mention that numbers, I don't know which numbers you had to do, but the ones down in the second block, you know how these are got 2 different blocks here? So the second block, the Maclaurin series is just a fancy word for Taylor series centered at 0. So this is actually a Maclaurin series. Maclaurin. If only I knew how to spell the name. Is it an I? It is an I. And there's only one C. Okay, get rid of one of those C's. I'll just do this. So Maclaurin series is just a Taylor series centered at 0. I guess we didn't have enough names for things, so we have that. So anyway, numbers 11, 13, I don't know which ones you had to do down there. You would just do a Maclaurin series. But I wanted to take a look at a different Taylor series just before we do the quiz, because this one, this one's not centered at 0. And so we're going to do the same thing, but we're centered at pi over 6. This is number, you had to do this one as well, right? Number 9? Number 9. So we're going to go through again. You're going to do your derivatives, cosine, negative sine, negative cosine. You start seeing a pattern, sine. In this case, you wouldn't have to go as far as I did because the first 4 non-zero terms will be above, will be these 4 up here. But anyway, now we're going to do the second derivative at pi over 6. So this is a great time for you to review your sines and cosines of pi over 6. So 1/2, radical 3 over 2, negative 1/2, negative radical 3 over 2, and then this repeats. Repeat. So let's put it all together. Maybe I'll put it up here in the middle. I'll do this a little bit quicker. So we have the first thing is just the function value. Then you take the derivative times x minus whatever point you have. Then you take the second derivative over 2 factorial times x minus the point squared. And then the third derivative over 3 factorial times x minus pi over 6 cubed. And of course, this repeats. And here again, since we know that this is going to repeat itself, we could probably write this in some sort of a closed form formula. It's not going to be as pretty as the one above, so I'm not going to attempt to do it, but it is possible. And it looks like there's some sort of an alternating. It's not quite as alternating as we'd like it to be, but I'm sure I could come up with something that looks reasonable. Yeah, you could simplify those if you want. This is going to be radical 3 over 12. That's going to be 1 over 4. So any questions about that? You know how to make your Taylor series? So neither of these did convergence, though, did it? Using definition. Yeah. Okay. Yeah, so numbers, the ones 11 through 18, same thing. You're just centered at 0. That's all. When it says use the definition of a Maclaurin series, it's just Taylor series centered at 0. All right, well, your quizzes are waiting for you on the printer in FA 101. So sorry about that. My wife says that at this point, we're all operating at about 50%. So anyway, there's the quiz there. So I wasn't going to collect it anyway because I still have a stack of quizzes from 2 weeks ago that I haven't graded. So I'll just give you all hundreds. But in the meantime, you can actually do this one. So you can see the general form. I was going to give you this so that you could have like the table like I'm going to do on the actual test, but too late now. So here's the, there. I should have written non-zero. So first for non-zero, just in case any of them are zeros. I don't believe they are, but there you go. First four non-zero terms. So go to it, and I will do it as well. And if you arrange your work sort of like I've done up here, you'll be, probably be able to do it more efficiently. Okay. And I apologize to, I'm going to interrupt you one more time, but I promise I won't again. I thought it might be helpful for some of you. Some of you are like, yeah, no problem. But for some of you, you might be looking at that cube root, thinking, how do I deal with that? It's just a power rule. So write it like this. It'll make your life easier. And I'll let you go to it. We just got started on this quiz. So basically, do what you can here. We'll go over it in just a few minutes. Well, I hear some murmurs, so I wonder if you're done. Why don't we go ahead and take a look? I was trying to check my work with my computer, but yeah, apparently it couldn't handle it, or maybe I just don't know how to type. So we'll see. So you'll have to yell at me if I get any of these wrong, because like I said, I'm working on about 50% right now. So first things first, I got my derivatives. So first derivative, pretty straightforward. Don't forget the chain rule. That's why this negative is here. So you're multiplying by 1/3, and then you change the exponent from 1/3 to negative. So subtract 1 from the exponents. You have negative 2/3, and then we're going to do that again. And so I got negative 2/3 times this is positive 2/9, but then multiply by another negative 1. So that's why these are all going to be negative. And then the next one, 10/27. There might be I was tempted to write this like 2 times 5 over 3 cubed, because I'm wondering if I could come up with a pattern, but then I didn't care. So I decided not to. The next one, of course, if I had done it, but I didn't need to, there's a blank there for a fourth derivative, but it would be, of course, 80 over 81, or negative 80 over 81, times 2 minus x to the negative, what is that going to be, 11/3? I didn't need that, though, because we only want the first 4 non-zero terms. And I realized also when I typed this up this morning, that notation is not correct for the first 4 non-zero terms, but whatever. We'll get to what that notation means, I don't know, later this week. So that's the fourth Taylor polynomial, which is different from the first 4 non-zero terms, but whatever. So the next one. So the next thing I did was I was computing the actual function values. So here's where, if you see anything that you think is fishy, let me know. So the key here, though, is that 2 minus 10 is negative 8, and the cube root of negative 8 is negative 2. So that first one, if you get that one, hopefully the rest of them are correct, but I did it all in my head. So if you see anything wrong, let me know. The next one I did that negative 2 to the negative second power. That's basically what happens here. So you end up with 4 in the denominator. So 1 over 3 times 4 with the negative looks like that. So far, so good? Does anyone have something different? Because like I said, I don't trust my mental calculator at this point. Probably should have done it on the regular calculator. Tried to get the computer to do it, and then it doesn't like the cube root for some reason. Okay, so next, here's what's this? Yeah, I just plugged in. So once again, 10 minus 2, or 2 minus 10 is negative 2. Negative 2 to the negative 5/3 is 1 over 32. Yeah, negative. So negative 1 over 32. The 32 cancels with the 2, so you get 1 over 9 times 16, which is 1 over 44. 144, yeah? So hold on a sec. You're talking about this right here. Okay, I'll double check because here's it's a good to check because, like I said, I'm only operating at about 50%. So let's do the derivative. So first things first, you multiply by 1/3, subtract 1 from the power, and then multiply by the derivative of what's inside. So doesn't that all end up being negative? Okay, yeah. So I did the chain rule. So chain. All right, no, it's good to check though, because I don't trust my brain any more than you should at this point. Anything else for these first 3 terms? Did I get my 1 over 144 correct? That look good? Good enough? Okay, last one. Yeah, and at some point I gave up trying to come up with a pattern. I'm sure there is a pattern. It's just that I didn't want to think about it at this point. So here, this one I did partially on the calculator. I guess, let me double check this. So essentially what I'm doing, here I'll tell you what I'm going to type in. So this 2 minus 10 is negative 2. Negative 2, or sorry, 2 minus 10 is negative 8. Negative 8 to the 1/3 power, so ignore the 8 there for a sec. Negative 8 to the 1/3 power is negative 2. So now I'm going to do negative 2 to the negative 8th power, which is the same as 2 to the negative 8th. And that's going to be 1 over 256. So 2 to the 8th, maybe I should actually type it in. 2 to the 8th is 256. That goes in the denominator. So I'm going to do 10 divided by, in parentheses, 27 times this. And then the negative is going to stick around. So let's see, I got this ugly decimal. Let's math 9 this, or no, math 1. Math 1. Yeah, 5 over, oh, I got it. Amazing. I did that one in my head, so I'm feeling a little bit better now. So far, so good. So there's my derivatives there. I'm plugging them in. As I mentioned, the ideal thing, we're not going to do this, but ideally, and I was thinking about this as I was doing it, ideal thing is to find a pattern so that once you have the pattern, you can write down sort of the general term of the power series, kind of the way I did down here. With this one, I was like, hey, there's a pattern, 1, 2, 3, 4. Easy. Up here, not quite as easy, but I'm sure there is a pattern. Once you have the pattern, you can exploit it and write it as a series. But this was only asking for the first 4 non-zero terms, so all I'm going to do is I'm going to copy down that first term, the negative 2, and then I'll take this thing, times x minus 10, and then the next one times, or divided by 2. So maybe I should have written that. Let me do this. So this is 1 over 144, all divided by 2 factorial. And then this one is negative 5 over 3456, all divided by 3 factorial. If I did, now that one I definitely did on the calculator. So if we needed a 5th term, but notice that they're all non-zero, so we're good. But if we needed another term, you would just take the next one down. Now, interestingly, if you were to, as long as we got this up here, if you were to graph, let's just cut this off somewhere, like that many terms is plenty. If you were to graph that many terms, you're actually going to be pretty close to the cube root of whatever this was, cube root of 2 minus x, when you're reasonably close to 10. You see all of these fractions, they keep getting smaller, so you actually are doing pretty good. Also, we haven't gone over it, but in chapter 11, we're going to learn that if you chop off the Taylor series like I just did there with that whatever color that is, that pink box, then the maximum error, the maximum how far you're going to be away from the truth is the next term. This is based on the mean value theorem, which we'll get into later this week. But so that thing, what I've got in the box, it's as close to the actual truth as this. This is the worst case scenarios, that you'd be that far away from the truth. I know it seems fantastical that you could predict how close you are to the truth, but we'll see this actually played out later this week. For now, though, the actual answer is the whole thing. I boxed those first three just as an example. Okay, so let's move on. Where are we? We're in PowerPoint land. Yeah, so we'll do as much as we can here. So, so just a quick preview. Let's see, where is the homework? I looked at it earlier today. I want to make sure that I'm going to hit the things that we're supposed to. Give me a sec. Find it. Homework zone. Homework, there it is, 41. Just a second. Okay, yeah, this is all good stuff. Okay. Yeah. Find the radius of convergence. Okay, so the radius of convergence is the main new thing. So there's two new things that we're going to add to the mix for today. So this is Taylor's theorem, Taylor series, and that's sort of the basis for everything that we're doing this week and next week. Well, next week is just one day. So we're going to add, and so you're already familiar with this. We're going to add two things to that. One of them is finding radius of convergence, or the interval of convergence, which is the same thing that you've been doing with power series. So that shouldn't be too shocking. And then the second thing is using existing Taylor series to come up with new ones. So that's a new thing. So let's just quickly mention the, let me find an example here. I don't like any of those. So we're going to go back to here. Give me a sec. This one. So let's go back here to this example, and let's pretend with number 5 that we were supposed to come up with, so here, I'll just zoom in here. Notice that this is the general term for this thing. So n equals 0, I'll write up here, e, this is x e to the x is equal to this, n over n factorial x to the n. So this is the Taylor series expansion for that function around the point a equals 0. And I want to know, what is the radius of convergence? Radius of convergence. So radius of convergence, all that means is that you're going to figure out the interval of convergence. So you have an interval of convergence that looks something like this. So here's A. A is always going to be, whatever A is, that's going to be right in the middle of the interval of convergence. And you're going to have some interval that is surrounding A. So you've got this interval. This is what we did with power series as well. You would come up with this interval of convergence. There was always a middle to that. You might not have noticed that there was, but there would have been. And then the interval is going to be something like this. The radius of convergence is going to be the distance from the center to the edge. So let me just, we'll come back to this one and we'll get this one, but let's just pretend. Let's suppose that your interval of convergence was this. So if that's the interval of convergence that you got from doing the whole ratio test and everything, if that's your interval of convergence, then the center, A in this case, would be 3. I hope you can figure out why that's 3. It's the middle. And the radius of convergence is 1. Let's just do one more, just for fun here. Let's suppose that, here, we'll do an actual series just to make sure that you see what I'm talking about. So let's do 2x over 5 to the nth power. Let's say that this power series, so this, we're just going back in time to when we were doing power series. See if you can find the interval of convergence for that. So find the interval of convergence for this thing. Probably I should have made it more complicated, but oh well. So take a sec, see if you can work out the interval of convergence, and I'll find a volunteer to help me out. That way I can check my attendance as well. I got everyone. It's okay. Now there's going to be a temptation with this one to just use the geometric series formula, which you already know. This is a geometric series, which is fine, but let's just use the ratio test just for practice, because that's what you're going to be using generally. Ethan, do you remember the ratio test? How do you set up the ratio test? I know, we're all operating about 50%. It's a ratio, and something goes on top, something goes on the bottom. Like up here, and you said n plus 1 up here, and then what goes on the bottom? The regular. Okay, which would be this. Oh yeah, that's perfect. Good job. So we're going to do that. And I want that. So the ratio test says that that's going to converge as long as that is less than 1. So let's go ahead and set this up. This is going to be the limit as n approaches infinity of 2x over 5. And that equals just 2x over 5. There's no in there to deal with, so it's constant, the 2x minus 5. So Ethan said that this has to be less than 1. So let's go ahead and set that up. And I want to know the interval of convergence. So let's do some algebra with this. Maggie, what kind of algebra do you want to do with this to get an interval? Very good. So multiply by 5, divide by 2. So I'm going to get something like this, 5/2 when you get done with that. Very nice. So we've canceled those and they end up on that side. So far, so good. Okay, last move. We need to do one more thing. Michael G., do you know what the very last thing for our interval is? Yeah, perfect. So this one was relatively easy because there was it wasn't x minus 2 or something. I should have made it more complicated, I guess. But there it is. That's the interval of convergence. The center of that interval is a equals 0, and the radius is the distance between the center and the edge of the convergence. So when you see radius of convergence, that's what it's looking for, is how far from the center can you go and still have this thing converge. So let me just go back up to the one that we did for homework, just to see how that works. Oh, no, better yet. Wait, can we? No, that one's not got a nice form to it. Yeah, I didn't bother writing down the form to this, the general formula. So we'll skip that. We'll go back to this one. Let's see if we can find the radius of convergence for this one. So this thing converges how far from the center? The center here is 0, by the way. So go ahead and do your ratio test. You're doing the ratio test with this. So limit n approaches infinity. I'll get it set up, and then we'll pick a volunteer. All right, Eli, set this thing up for me. What do I do for this to get the ratio test? Okay, so like this. N plus 1 factorial. All right, so far so good. And then what? The regular one, which is just you put in. There we go. Very nice. Let me simplify this before we set up an inequality. We want that to be less than 1, just like the last time. Ugh. Okay. See if you can figure out the algebra that got me to that step there. I kind of skipped 3 steps. I can explain them one at a time, though. But see if you can work it out. That all of that, after you flip and multiply and cancel, you get to this. So just in case you're still looking at that saying, where in the world did that all go? Let's just point out, let me use a highlighter, hold on a sec, that of course the easy part is this, that you combine those two and you're left with just x. So that's the easy one. Now, what about the rest of this stuff? Well, presumably that in that you're looking at over on the right, that in is this in, you would think. And yeah, that's great. You can say that. So what about the rest of the stuff? Apparently it all cancels. Well, let's see how it cancels. This in factorial, when you get done flipping and multiplying, that in factorial gets multiplied by that in plus 1. And in factorial times in plus 1 is in plus 1 factorial. So these two that I've highlighted orange will cancel with this one that I'm going to highlight yellow once I get my pen changed. So the two orange ones combined, they cancel with the yellow one, and that in is the only thing left. So if you believe that, then I guess we'll be happy. Now we got to do our limit. Landon, what is the limit as n approaches infinity of this thing, as long as you believe that my algebra is correct? It's 0. Oh, yeah, it is 0. It is 0. And 0 is less than 1. Notice that it doesn't matter what x is. X can be any number you want, and this is always going to be 0, which is less than 1, which means that this thing converges. You say, well, what's the radius of convergence now? It converges for all values of x. X can be anything, and so we say that the radius of convergence for this is actually infinity, because it can go as far as you can start at 0 and go, the sky's the limit. It's going to converge everywhere, which is incredible to me, that you could have a series that converges for every value, no matter how big the x is, because x to the n gets really big, but the in factorial kind of tamps it down. So there's that. So that's one of the things you're going to have to do is, I mean, half of the homework is basically doing what you did for today, coming up with Maclaurin series. But in addition to doing the Maclaurin series, you'll do this, come up with your radius of convergence. That's all that's referring to. Then the other half, what you're going to be doing is you're going to build series from series that you already know. We've already done this. Let me just show you. You did this already with our favorite power series. At least it should be your favorite power series, and that's this one. 1 over 1 minus x is equal to 1 plus x squared plus dot, 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 which is just this. So this is your favorite. Well, maybe it's not your favorite, but it is the one that we've been using almost exclusively up until now. So, so anyway, if I had something like this, then you would say to me, well, all you have to do is replace the x here with negative 2. Here, I'll write it down. 1 over 1 minus negative 2x squared, which now I'm just going to replace that x up there like this, negative 2x squared. And then I'll need to do some algebra to make this look pretty. But other than that, I'm pretty much done. So you're familiar with this technique. Well, we're going to do the same thing with other power series. In fact, take a look at this power series. E to the x is equal to this sum of x to the n over n factorial. Oops, I don't need another equals there. So that's the Taylor series for e to the x, power series if you want to call it, and it converges for all values of x. So interestingly, converges for everything. So what we could do, if we know that this is true, so this is true, I'll show you where to find this in the book in just a minute, but this is true. This is one of my favorite power series. In fact, it's so much my favorite that I actually printed it on a t-shirt to give to one of my daughters. I'll show you that picture in just a minute. But anyway, so this particular power series, if I wanted to come up with the power series x e to the x, I would just take this power series and multiply it by x. Check it out. There we go, which is equal to x to the n minus 1 over n factorial. So let's see, n goes from 0 to infinity. Oh, I'm sorry, plus 1, shouldn't it be? Plus 1. There it is. That's the power series for x e to the x. And we did this actually up here. Where is it? There it is. Yeah, there it is. X e to the x. You might say, well, that doesn't look the same. Well, if you do a little bit of algebra, change the index a little bit, you'll actually get exactly the same expression down here. Same expression. Okay, so let's go back to PowerPoint because I know you want to see those pictures, don't you? Okay, so first off, here's Euler's formula. Okay, first of all, this. So some of my favorite Taylor series. You might say, where are these Taylor series found? Because you want to memorize these as well. Why is it so dark? I don't know why it's so dark. I'll see if I can correct that up here while I'm blabbing about it. So in your book, you will find, actually these are Maclaurin series, they are not Taylor series. You will find this list in your book on, let me find the page, there it is. It's on page 768. You'll find a list of a number of power series, or Taylor's, actually they're Maclaurin series. I keep changing the name. They're Taylor series centered at x equals 0, and we can use these as building blocks for other Taylor series. That's the beautiful thing about this. So just a minute and I'll see if I can change the background on this. Why? Yes, I don't know why it's red. Change background, just a sec. Solid. Let's go with white. Okay. Let's see if that, oh, that's much better. So much better. Let me change this one as well. And change this one. Sorry, you can't see the one that I'm changing, but it's purple. I don't know why it's purple. That's much better. Okay, so we'll go to the purple one in a bit. But for now, so here, these, like I said, many of these, not all of them, there's others, they're found on in this table on page 768. And so you might say, well, how are we going to use these? Well, the way that we're going to use them is, maybe I should use the ones printed in the book on page 768, is suppose that we want to come up with the Taylor series for a function that is related to one of these. For, not that one. Let's see, go back to here. So let's do this. Let's do the sine of x squared. We'll do that one first. So the sine of x squared. So we'll start off as a building block. We'll start off with this, the sine of x. The sine of x, according to this table, I just want to do it the exact same way that they have it here. So, because the way that I've got it memorized might be a little different. X to the 2n plus 1 over 2n plus 1 factorial. There we go. So there's the sine of x. And so if you want the sine of x squared, all you're going to do is you're going to take x down here and replace it with x squared. So here we are. Negative 1 to the n times x squared to the 2n plus 1 over 2n plus 1 factorial. And now we need to simplify just a little bit, though, not bad. So this will be this sum -1 to the n, x to the, whoops, multiplied by 2. So this will be 4n plus 2 over 2n plus 1 factorial. Let's look and see if there's any others that we need to do. So just a sec. So we're almost to the point where this actually is going to help us out. Well, we could do it right now, I guess. So without getting all of the stuff together, the normal curve, so you're probably familiar with the normal curve from statistics class, is related to the e to the negative x squared. It's not exactly, there's a e to the negative x squared over 2 or something like that, and there's a 1 over 2 radical 2 pi out here. But let's not worry about that too much. What I want to point out is that if you try to integrate this, which you have to do when you're doing statistics, if you're trying to compute areas under a normal curve, you're going to be basically doing areas like this. The issue, though, is that this doesn't have an elementary function antiderivative, and so you can't do that. But we can do it using series representation. So e to the x is going to be this summation. So this one, I know I've got memorized the same as the book, so I won't bother looking. So that's the Taylor or the Maclaurin series for e to the x. And so if I want to do e to the negative x squared, all I'll do is I'll change the x here to negative x squared. And that's going to be -1 to the n, x to the 2n. There we go. So technically I did -1 times x squared, and then I raised it all to the n power. Now the reason why I point this out is because now I can take that and I can do the antiderivative of that by basically doing so once again, you've seen this before, not very exciting, but I can do the antiderivative term by term. So this will be the antiderivative of this sum. -1 to the n, x to the 2n over n factorial. And this is easy because you all know how to do polynomials. So, it is time. Okay, thank you for that. So let's see. So this is going to be this sum. Yeah, we got to get the pictures. So -1 to the n times, so we're doing the antiderivative. So that means add 1 to the power and then divide by that power. So you might say, well, there's a plus c that comes into this. So how are we going to use this? Well, if we're doing an area under a curve, you might do something like this, the area from 0 to 1, 0 to 1, and then you're just going to have to evaluate this between 0 and 1, which means plugging in 0, which is easy. 0, you just get 0, because this is, plugging this in. But when you plug 1 in, you're going to get a summation, a series. It's an alternating series, and you could approximate the value of that alternating series. And that's, in fact, what is done to come up with the tables in your statistics book or online when you're doing a normal curve. All right, so let's see, one more thing, and then we'll get on. So one of the reasons why these are some of my favorite power series is because of something called Euler's formula. Euler's formula takes those three. So if you see those top three, let's see, are they printed exactly the same way in your book? I want to make sure. Yeah, they are. Okay, good. So it takes those three and says, hey, Euler noticed there's a relationship. Do you see the relationship? I don't know if you see the relationship, but this one has 1x, x squared over 2, x cubed over 6, and so on. This one has x cubed over, well, wait, it's the same things. It's just missing the odd, or no, this one's missing the even terms. And this one down here, the cosine is missing the odd terms. I don't know if you've ever heard this, but cosine is an even function. So in pre-calculus, you might have learned even functions are symmetric around the y-axis. Odd functions are symmetric around the origin. And here's one of the reasons why sine is odd is because if you look at its power series representation, it only has odd powers. Cosine is even because it only has even powers. Also, you'll notice that the everything looks the same. It's almost as if you could take a sine and a cosine, add them together to get an exponential. Almost. I mean, the problem is that you have minuses here that aren't up there. But interestingly, Euler figured out a way to combine these three formulas in this beautiful way. So check it out. If you take e to the ix, then, and you know what I is? I is the square root of -1. If you do e to the ix, you get this expression. And then if you take this and sort of separate out all the i's, and remember that I squared is -1, I to the fourth is +1, I to the third is -I, and I is right there. Anyway, you can separate things out. Okay, there it is. And you'll notice that all of the even terms don't have i's. The odd terms do have i's, but check it out. The odd, if we do the odd terms, no, the even terms, 1 minus x squared over 2, that's exactly what's at the top of the screen. And then plus x to the fourth over 24, exactly at the top of the screen. So if you take the even terms, you get cosine. The odd terms are a little bit odder, but they're not too bad. So take these things, those and those, together, you get cosine. The odd terms, you get I times sine. And so what Euler's formula is, and I'm surprised it's not printed here, but here's Euler's formula, and it is e to the ix is equal to cosine of x plus I sine of x. We have the mower. Oh, sorry. Oh, I hope they go by again. Just a minute. Okay. I got to get my camera ready. It's an inside joke you don't need to know about. Okay, so now here's a super cool thing is do e to the I times pi, and you get cosine of pi plus I times sine of pi. It's going the wrong way. That's all right. And so that's e to the I pi is equal to -1, because sine of pi is 0. Buddy. Oh, here he comes. Here we go. Oh, wrong way. Okay, this is the best I can do. All right, sorry. My daughter was visiting over the weekend, and we were talking about this phenomenon. So she's at Gordon College, and she says this happens all the time. So it's like, yeah, it happens all the time to me too. But anyway, so the final. Sorry about that. Plus 1 equals 0. So this formula, mathematicians love it because it has all 5 of our favorite numbers. You have e, I, pi, 1, and 0, all in the same formula. Now, this is such a cool formula that like I said, I made T-shirts for my family for this. So here's one daughter. She has, which one is that? That's the cosine. So that's my oldest daughter has the cosine on her shirt. And then the middle daughter has the sine. She's a little shy. And then the youngest has e to the x, and then I have the theorem, which is yeah, but you can't. Yeah, she's excited about her shirt. So my shirt, I guess I don't have it here. My shirt has the formula wherever it is. There it is. That one on it. And actually, let's see, my oldest daughter got married, and my son-in-law was jealous that he didn't have a shirt, and so I made him a corollary to her theorem. But anyway, so on your homework, what you're going to be doing is you're going to be using these Taylor series. Remember to look on page 768 for the table, and you'll find them. I'll see if I can find. I've got a family photo with the corollary as well. So I'll see if I can dig that out of my files. But for now, I think you're good for your homework, and we'll see you tomorrow. Stick around if you want to chat. I'm going to stop the